I guess, do I have to repeat everything now? I mean,
No,
um,
I guess it's fine. We can go for
uh-huh. Because I think I want the message to go out that I want people to do a lot of reading on their own. So, coming back to um, what I was talking about, we are basically trying to estimate. So, essentially, the relationship that we have is that KLA CO star minus a CO at steady state, right? This has units of millimoles of oxygen consumed per liter of the reactor per hour. And if this is multiplied by the total volume of the reactor, then this is telling us the rate at which oxygen is being consumed in the entire reactor. And that has to be equal to Fg in multiplied by Cg in minus Fg out multiplied by Cg out, where Cg is the concentration of oxygen. Yeah, we're dealing with oxygen here. And if that, and basically now to this equation, if you apply the ideal gas law, that is to say, for instance, if I write Cg in as equal to P in multiplied by Y in divided by RT times in, and similarly, I write the equation for O2 going O2 out, and the Cg out as P out multiplied by Y out divided by RT out. That's the equation that I'm working with. And we estimate this on the right hand side, we are estimating the difference between oxygen in and oxygen out. And if we divide that by the total volume, it gives us KLA CO star minus CO. If we know CO star and we measure CO, which is the concentration in the reactor, right? This is in the on the left hand side. Keep in mind CO star and CO refer to concentrations in the liquid phase. Then we can calculate KLA. And so that's what the numerical problem is. I thought, if I remember correctly, it was example 10.2. But anyway, solve numerical problem showing how KLA is calculated. Now, the second thing I told you, which was exercise 10.8, the reason why that is important is now you can see that anytime you try to do a calculation that is based on determination of the difference between two quantities, as is the case here, we're trying to measure the difference between uh, second. We're trying to measure the difference between the first quantity and the second quantity. Now, if the difference between these quantities is very, very small, then, in practice, you're kind of doomed. It'll never work. Yeah. So, I mean, I won't go into the technical details, but I'll just mention at the top, for example, imagine you are trying to measure the difference between two quantities, one of which is 100 and the other is 99. In the ideal mathematical world, this is very simple. This is 100 minus 99 equal to 1. But in the practical experimental world, this is not 100, but this is 100 plus minus some error. Let's say it's 1. And the second quantity is not 99, but it is 99 plus minus 1. Now, so you can see that when the errors, right, when these errors are on the order of the difference between the two quantities, right? I mean, if your error is 1 and the difference between the two quantities is 100 minus 99 equal to 1, then your measurements are on the order of the errors. That means you're going to get 100% error. And that is what the problem shows. It turns out that under certain conditions, these differences are small. So when you try to measure them, in practice, you will end up with garbage. Let me just pause and ask if this is obvious. Is that clear? Whatever I've done?
yes,
Yes,
sir.
sir.
Okay. But this idea will become much clearer to you if you take a look at the problem. I should mention that, by the way, this um, concept that I have just mentioned, This one, it appears in many places in science. I mean, experimentalists actually know this very well. Uh, so I'll give another example, uh, which is also relevant. Actually, you'll end up using it in your practicals. Another example of this is, how do you actually measure the concentration of cells in a bioreactor? Well, the way you measure them is essentially, you take the cells out of the reactor and you put them on a filter paper. Okay, so you put them on a filter paper. So this is your filter paper, and then you have some samples. Let's say you took 2 milliliters with a pipette, and then you pipette this stuff onto the filter. The medium goes down, and you trap all the cells on the filter. Then you basically take this filter with the cells, um, essentially heat it up, dry it, and basically calculate the mass of filter plus cells minus the original mass of the filter, which you have already weighed before you start the experiment. So in this case, you are measuring the difference between filter plus cells minus filter. And in this case, once again, you have to simply make sure that you have enough mass of cells on the filter that the difference between filter plus cells minus filter is substantially bigger than the errors of the measurements, right? So you want to put a lot of cells to make sure that the mass of the cells is well above the error of your measurements. So this is another example. I mean, you could go on and on. This is something that appears again and again, and um, it's just a good thing to understand the basic idea. So try out problem number 10.8. Okay.
So approximately to what temperature are those cells heated up?
It is, boy, I think I can dig it out for you. I don't have the number off the top of my head. It is basically to evaporate. Uh, you just want to make the moisture disappear. So that's why it's called dry weight. So it is not very high temperature. You're not trying to volatilize anything. You're simply trying to heat it up to the temperature. I mean, I can dig it out for you right now. Maybe I'll look it up and send it to you. I mean, I have it here in my notes, but I actually kind of okay. Let me just spend the time and uh, can we just do this later on?
Yes, sir. Sure, sir.
Uh, I really think that the topic I'm supposed to cover is far too important to be missed. So that brings me to the first topic, which is fed batch reactors. So let me define this and then first say why it is important, right? So define meaning, what is a fed batch reactor? Well, a fed batch reactor is something between a batch reactor and a continuous reactor. So for instance, in a batch reactor, we had neither an inlet nor an outlet, right? It's just a closed system. It's exchanging mass, it's exchanging gas with the surroundings. There's air coming in and air going out of the reactor. But no, the liquid medium just comes in. It never goes. I mean, you start it and then you never allow anything to come in, never allow anything to go out. In a continuous reactor, you have both uh, a flow in and a flow out. So a batch reactor is actually something in between, in the sense that it has a stream of feed going in, but it does not have any outlet. So there is no outlet. This is not there. The effluent stream from the continuous reactor is absent from a fed batch reactor. So that's actually what is a fed batch reactor. Now, why is it important? Well, uh, see, the most uh, versatile reactor is the continuous reactor for a very simple reason. Um, in a batch reactor, the cells always grow at the maximum specific growth rate. So you have no control. I mean, or the only growth rate at which you can grow them is the maximum specific growth rate, which may not be the best, right? I mean, it may very well be the case that perhaps they do your job, and this is often the case. They actually do much better at growth rates much lower than the maximum specific growth rate. But the batch reactor is giving you no control at all. If you go to the continuous reactor, I mean, this it gives you all the control you want because you can choose your dilution rate, which is basically just the flow rate, to any value you want, and the cells will automatically adjust to that value of the dilution rate because the specific growth rate is equal to D. So you can choose any dilution rate you want. So clearly, the CSTR is much better than the batch reactor. But and one more thing is, I think, and this was part of the numerical problem you solved, the volumetric productivity of a continuous reactor is also much higher than that of a batch reactor. And actually, I think nobody answered that question properly. The simple reason is that uh, in a batch reactor, you have a long period of time when the cell density is very small, right? Because they go from a density of 0.05 to point 0.1, and then point 0.1 to point 0.2, then point 0.2 to point 0.4. Whereas in a continuous reactor, after that initial transient, you're always maintaining high cell density. And roughly speaking, the volumetric productivity, which is the rate of production of biomass per unit time per unit volume of the reactor, is essentially proportional to the cell density because the more cells you have, the faster they grow. So, in a batch reactor where they spend most of their time at very measly low cell densities, there's hardly any biomass being produced most of the time. Most of the biomass is produced right at the end when the densities are high, but in a continuous reactor, the densities are high all the time. So that's why the volumetric productivity is much higher. This is the answer to the question that was being asked in the minor and actually in your homework problem. So if that is clear to you now, with all these advantages of the continuous reactor over the batch reactor, you have to ask why they don't use the continuous reactor. Well, two main reasons. So why um, why don't they use it? And then I'll tell you what is the latest. I mean, people's minds are changing now, and this is sort of very much at the cutting edge. So, uh, so why not use continuous reactors? Which are called CSTRs in the chemical engineering literature. Well, the first reason is the fear of contamination. You know, and this is basically saying that you run a continuous reactor for like 30 days. A fed batch reactor, you have to stop. Keep in mind you're flowing the stuff in, so as soon as the reactor fills up, you have to stop. But a continuous reactor can be run forever. A batch reactor runs only for as long as maybe 2 days. I mean, and then you have to stop. Well, if you run a reactor for like 30 days, there's always a slim chance that from the piping and so on and so forth, contaminants can go in. This was always the fear of particularly the biological people. Another fear is that when you run the reactor for so long, the theory of evolution is at work in the reactor. Stuff mutates, and these mutants are fitter than their parents, and they grow faster, they survive faster, they survive better, and quickly displace. So next thing you know, 15 days later, you might actually have a strain that is not making the stuff that you inoculated. It is not making the product because it has completely displaced the strain with which you inoculated the reactor. And the third one is, you know, regulatory issues. And by regulatory issues, I mean that bodies like the Food and Drug Administration in the US and the similar one in Europe, I don't know which one it is in India. These regulatory bodies, they decide, uh, they're very strict. They used to be very, very strict. So they would say that I want to know every time you make a drug, I want to know which batch was this drug made in. So every time you run your batch reactor, you have to document exactly which batch. And there is a number when you buy anything, it'll say batch number so and so, right? So now, the moment you define drug quality by a batch, you're almost compelled to run only in batches, right? In a continuous reactor, the question becomes, what the hell is a batch? I mean, it's running all the time. But now, this body seems to have finally accepted the simple logic that in a continuous reactor, a batch is nothing. That's something you collect between two times. So anything you collect between, say, day 7 and day 9 is considered one batch. Anything you collect between from the effluent stream between 9 and 11 is also a batch. So now this has disappeared. This problem has disappeared. Uh, if you read the paper, which I gave to you for your minor one, that paper was written, I think, in 1956. That paper repeatedly says that we had no problem with contamination and no problem with mutation. So actually, if you run sensibly with a half a brain on your head, you shouldn't have any problem. But I think the biologists completely dismissed it. I mean, they just wouldn't buy it. And so they had this unfounded fear for several years that this would happen, even though there was ample evidence that it could be controlled by careful operation. And today, actually, a drug like insulin is made by this company called Novo in Denmark entirely in continuous reactors. I mean, they run it for a month, nothing happens, everything is fine. So there is growing acceptance for the use of CSTRs because all the problems associated with it have disappeared. And since they have much higher productivity, people just want to use them. But there are other problems associated with it. I mean, the main problem currently right now is you are, if you run a CSTR, you're making the protein continuously, right? But you must also have downstream processes for purifying the protein also that should run continuously. Well, it turns out that many of the downstream processes for purification, such as chromatography and centrifugation, I mean, these are not run very well in the continuous mode. So until these processes are also made continuous, the CSTRs will remain an object of laboratory research, but not industrial production. So,
Sir,
uh-huh.
sir, can't the proteins be stored at low temperatures with protease inhibitors and all that?
Yes, they can be stored. Why is that important? I'm trying to understand where is that question coming from.
Like we can use CSTRs and then store the protein so that it can be purified in a batch manner.
So that's being done. I mean, some people are doing that, but that's not a real continuous process, right?
Yes,
So,
sir.
so actually, if you go and take a look, there's this guy in chemical engineering working on it. I think the word they use is continuous bioprocessing. They don't use continuous bioreactor. So keep in mind, this course is dealing only with the production of the protein. It is not talking about its downstream purification. So maybe I'll put this paper out there. You see, sometime in 20, I would say, when was it? So so what happened was that people were harping about this. We need to shift to continuous. We need to shift to continuous. There are actually reasons for it. The reason is kind of simple. Actually, if you run the system in a continuous mode, I mean real continuous, right? Not the one that you mentioned where half of it is continuous and half of it is batch. That people are doing, but that does not give you the full advantage. The real advantage of a continuous process is that actually when you run things continuously, because the volumetric productivity is say like 10 times higher, the size of a reactor is 10 times lower. And that means that the footprint is small. Two, ironically, it is actually much easier. So another problem which I've not mentioned is, making these therapeutic proteins like vaccines is not like making petrol, right? I mean, it's not like making gasoline that you make like millions of gallons, a month. You make them like 5 kilos per day. That's the scale on which you're making it. It's so small, some proteins, that the scale is really, really small. So in this case, actually, it turns out that actually these small reactors are quite good. Run them for like 3, 4 days, make protein A, then shut it down, clean it up, feed in the next protein, and make the next one for the next 7 or 8 days. So all these things taken together are pushing the manufacturers towards CSTRs. But as it stands today, they still use fed batch reactors because they feel that they can overcome problems A, B, and C also, because a fed batch will ultimately produce just a batch, right? I mean, you basically keep on running it until the reactor fills up. When the reactor fills up, you stop. That's your batch. It has a well-defined number, which you provide to the regulatory agency, and that's how your drug comes out. So if that part is clear as to why you use fed batch reactors today, because of, I mean, in my opinion, a perceived fear of factors A, B, and C, mostly. There are other reasons too. Then I can move on to the theory. So is that part clear?
Yes, sir.
Uh, so
Yes,
now,
sir.
let's get to the theory. So, I mean, actually, like I told you, everything can be understood in terms of CSTRs. And the two main points I want to illustrate. So, the two main points to be illustrated. So, the first point is, so keep in mind that this flow rate, which is coming in, right? There's only one flow, which is the flow coming in. This flow rate is completely in your hands, right? I mean, as an operator, you can do whatever you want with it. And it turns out that two particular uh, f of t's, in other words, the variation of the flow rate with respect to time, two particular examples of it are especially important. The first is, they are known as exponentially, exponentially increasing flow rates. If you choose this f of t, so in other words, f is increasing exponentially. Yeah, replicate CSTRs. By replicate, I mean that basically, you give me a value of d in a CSTR, and I can choose f of t that is growing exponentially at with the exponent e to the power dt, and that fed batch reactor will give me exactly the same steady state as the one that I got in the CSTR at the dilution rate D. So, since it can mimic or at least replicate what I can get in a CSTR, well, it's kind of nice that I find an optimum, I do some lab studies, find an optimum dilution rate by doing my experiments in a CSTR. Then I just move over to the fed batch reactor, operate it at f of t equal to f0 initial flow rate e to the power dt, and you will find that it will give you exactly the same steady state as the one the CSTR gave you at that dilution rate d. This is what we want to show. The second thing we want to show is that constantly increasing flow rates. So this means that f is directly proportional to time. So it's increasing linearly. Constantly increasing means maybe I should say linearly increasing. This is another common method. These, uh, you know, uh, what we will see is trace the steady states of a CSTR. And what I mean by that is we already know that for a CSTR, so keep in mind we are talking here about the concentration of the feed is fixed. We are not changing the feed concentration. We are only playing around with the flow rate. Okay, that's the picture we have in mind. So let's say that we have the CSTR produces, let's take the simplest model that we have covered, the Monod model without maintenance. And let's say this, if you remember, is the picture with this being the biomass and this being the substrate concentration. Now, what we will find out is that in a constant fed batch reactor, basically what is happening is that you are starting from some D0, and this D0 is decreasing from its initial value D0. So when you start the fed batch culture, you have a certain dilution rate, and the dilution rate decreases very, very slowly. So slowly that you basically trace all the steady states of a CSTR. These are the two things that we want to show. So let's start by looking at the mass balances. So how will we show this? So the first thing that I want to show is this is obvious. This relationship is kind of important. Um, this is the total mass balance. By the total mass balance, I mean I'm taking a look at in the liquid phase. So basically, the rate, let rho be the density of the material that is inside the reactor, and V be the volume of the liquid phase in the reactor. So rho multiplied by V is the total mass of the liquid phase that is inside the reactor, and we want to see its rate of change. Well, this rate of change, there's only one stream coming in, which is coming in at the flow rate F, which may very well be a function of T. It's not necessarily constant. Um, and so multiplied by rho times F, which is the density of the feed. So this has units of, say, liters per hour, and this has units of grams per liter, right? So this is essentially grams per hour, right? This is the mass flow rate. The rate of change of mass of the reactor has to be equal to the rate of mass flow into the reactor. Now, as I have pointed out repeatedly, in biological reactors, right, the stuff going in is basically pure liquid. The stuff going out is liquid plus cells. But since the density of the cells is essentially equal to the density of water, the density of cells is like 1.05 grams per centimeter cube. The density of water is 1. So rho F, which is, rho, which is the density of the water plus cells, is actually very close to the density of the feed, which is actually equal to 1 gram per centimeter cube, approximately, right, depending upon the conditions. So since rho is equal to rho F, you arrive at the relationship so that you can say, some people use this without even thinking about it. You arrive at the relationship dV dt equals F of T. I mean, many people would use this intuitively without even giving it a thought. So I want to actually make a correction here. This was wrong. This is not linearly increasing, but this is constant flow, not so F is equal to constant. So we are looking at one case where F is increasing exponentially and the other one where F is equal to a constant. So the first case they're called exponential fed batch cultures. The second one is called constant fed batch cultures. These are the two cases we want to look at. So now that this mass balance is clear, let's move to the second one. And actually, the main thing I want to show is that the mass balance actually looks formally identical to that of a chemostat, which is kind of really seems a little puzzling. But once you understand that, you will understand the link with. So let's take, you see the link with CSTRs, mass balance in a fed batch reactor for cells. So for cells, we're going to first take a look at how does the total biomass in the reactor change, right? So the cells, of course, live in the liquid phase. The volume of the liquid phase is V, and the concentration of the cells is X grams dry weight per liter. So this is grams dry weight per liter, and this is, of course, in liters. So the left-hand side has units of grams dry weight per unit time. So this is the rate of accumulation of biomass in the reactor. And on the right-hand side, we have only an inlet stream, and no outlet stream. Now, so basically, there is an inlet, but no outlet. But the inlet is sterile. So actually, we have F, but Fx, so this is the flow rate. Now, this is equal to 0. That means there's nothing coming in. Since there is no outlet, there is nothing going out. The only thing that you have is actually the generation of cells within the reactor, which is mu times X times capital V. Is that part clear? So if this part is clear, I can move on to the next one. Is there any question about the mass balance that I've written?
No, sir, it's pretty clear.
It's clear.
So now starts the sort of tricky part. Now, in a chemostat, volume was constant, right? We made sure that the flow rate in is equal to the flow rate out, and therefore we kept the volume constant. In a fed batch reactor, you can already see, since there is no outlet and stuff's coming in, obviously V is increasing with time, right? There's no, in fact, you can actually find out, you can see right away that if my initial, from this equation, you can see that it will be V0 plus integral of F of tau d tau from 0 to t, right? It's obvious that volume is increasing with time, where V0 is my initial volume, right? This is initial volume. So just integrating this equation, you can see right away mathematically or intuitively, you can see obviously V is increasing with time. Since V is changing with time, you can't pull it out of the derivative. So you use the product rule. If you use the product rule, what you find is you get V times dx dt and then plus x times dv dt, right? But that plus x times dv dt, I'll move over to the right hand side. Okay. So this, maybe I should just do it. So this is plus x times dv dt, and that is equal to, I have on the right hand side just mu times x times v. Now, dividing through by v, that's permissible, even though volume is a function of time. This tells me that I can write this as dx dt equals, right? You get mu times x, right? Because I've divided through by v minus x multiplied by 1 over v, 1 over v dv dt. Is that part clear so far? Now,
Yes, sir.
the important point here is that we have come up. So let's actually proceed a little bit further. Well, dv dt, we just showed above, is nothing but f, right? F of time. That's what we call, this is the related to the rate at which the volume increases is related to the rate at which stuff is coming into the reactor. Well, that being the case, I can write this as dx dt equals mu x minus x times, well, I get an f of t over v. And that, if you remember, is nothing but formally what we call the dilution rate, right? This was the dilution rate in a chemostat was defined as the flow rate over the time, and we will maintain the same definition. And it makes kind of good sense. Well, why is it why is this related to the dilution rate? Well, um, eh, so first of all, let's try to understand what's going on here. Formally, the equation looks just like the equation. I mean, if I didn't put a d of t here, right? If I didn't put, you could hardly distinguish this equation from the equation we derived for a chemostat, right? It looks exactly the same, mu x minus dx. So the question arises physically, what's going on? In a chemostat, this quantity dx came about because there was an effluent stream which was carrying the cells out of the reactor. In a fed batch reactor, the very same term is coming about, but it is coming about because the volume of the reactor is expanding. And that expansion of the volume, the liquid volume in the reactor, tends to dilute out the cells. I mean, the faster the volume grows, the liquid volume grows, the more difficult it is for you to maintain the concentration of the cells. They just tend to dilute out. So the formally the equations look the same, but the interpretation of D is, in one case, you can see that in this case, the D represents percent volume expansion of the reactor, right? 1 over V dV dt is the rate at which the fractional increase of the volume per unit time. So the main point to be made is equation looks formally like the one for the CSTR. Okay. Now let's proceed a little bit further and see if this is the same for the others. So I will do one more and then you can try out the next one on your own. So let's take a look at the mass balance. So although they look formally the same, but keep in mind the interpretation of D is different, right? In the case of a chemostat, D represents is a measure of the flow rate coming out of the reactor. The same quantity D represents a measure of the volume expansion in a fed batch reactor, right? But the definition is the same. It is D is equal to F over V. Now mass balance for substrate will also give an equation that looks exactly like the equation for a CSTR. So let's start. We have ddt of S times V. This is the total amount of substrate in the reactor. Now we have stuff coming in, right? So there is F times SF. but we have nothing going out, right? The flow rate out is 0, so there is nothing going out. And of course, we are consuming the substrate, so that is minus Rs times X times V. This is the consumption rate. So we have an in and we have a consumption, but we have no out. Once again, use the same trick. You can't pull V out, and you can write it as essentially V times ds dt. And now we'll skip one step. Just move that term over to the right hand side. You get this here, you get F times SF. And on the right hand side, you get minus Rs times X times V, right? Minus S times dV dt, right? I've just moved that over to the right hand side. Well, divide the whole thing by V and you get ds dt equals, this is F times SF, and I'll move this term over to the second term and I will write it as minus S times 1 over V dV dt, right? So I have to write this as F over V, and that is S times 1 over V dV dt minus Rs times X. Now notice once again, this quantity is F. So once again, I can write this equation as ds dt equals d times sf minus s minus rs times x, where d is nothing but f over v, but you have to remember that f is a function of time, it's not a constant, and that this quantity d is actually a measure of the volume expansion. In fact, it is nothing but 1 over v dv dt, which means it's the rate at which the rate of increase of the percentage, it's like 1 over v dv dt. So it's the rate at which the fractional increase is taking place. So is that part clear now? You're getting the same equations. And that's kind of really, really bizarre, but actually the only thing that has happened is you have replaced the exit stream by a volume expansion. That's all that's happened in a fed batch reactor. And that is the reason why there is an intimate connection between fed batch reactors and continuous reactors. Every time you do something in a fed batch reactor, you are basically replicating something that's happening that can happen in a continuous reactor. So, I will let you do this triad on your own. So mass balance for product, you try it on your own. So you can try on your own, and you will find that even that will look like the balance for a chemostat. Now this information taken together now allows us to understand what main points. The first point is what I called exponential fed batch cultures. Replicate. So the first point I wanted to make was exponential fed batch cultures can replicate continuous cultures. So what do I mean by that? Now, coming back to this equation, right? Say take the first one, right? This is, keep in mind, 1 over V dV dt, right? Now, suppose I tell you that, I have done some experiments and, I found that a D equal to 0.1 per hour is the best dilution rate to work at. This is based on my experiments in a CSTR, right? I ran a continuous culture. I tried out a whole range of dilution rates. From among those dilution rates, I isolated D equal to zero point 0.1 per hour as the optimum dilution rate that I want, that one should use. And I'm an academic, and you're an industry guy. You want to operate the fed batch reactor such that the same steady state is reproduced in your fed batch reactor. What particular, how will you do it? Well, it's pretty simple. Take a look at this equation that I'm marking out in red. Right? This is the equation that defines the dilution rate in a fed batch reactor. I will set D equal to 0.1. If I set D equal to 0.1, I basically get 1 over V dV dt is equal to 0.1, which basically means that every per unit time, I increase the volume by 10%, right? So this is exponential increase. So essentially, if I run the fed batch reactor such that the volume of the reactor increases exponentially, and if the reactor has to increase exponentially, that means, ultimately, why is the reactor volume increasing? It's because of the feed. That means the feed must be increased, the flow rate in must be increased exponentially. And if I do that, then I will get a constant D. If I get a constant D and I put it into this equation, then in the long run, the system will come to a steady state. That steady state will be identical to the D equal to 0.1 that I had seen in my continuous reactor. Is that part clear? You got the idea?
Yes, sir.
Yes, sir.
Is there anybody who didn't get it? The whole point is actually for people. Um, is there anyone who has a question where it was not clear? Okay. So now that you understand it, let's just flesh out a couple of details, which is, so all we do is, so given any D in a CSTR, right? Actually, let's give it a different symbol. Let's just call it D. I don't know. Let's call it DCSTR. We can replicate that's the corresponding steady states, and by corresponding I mean the steady states that have been observed in the CSTR at D equal to DCSTR. So we can replicate by operating the fed batch reactor FBR such that 1 over V dV dt is equal to D CSTR. And if my initial volume I denote by the quantity V0, then that means that this is essentially saying that V as a function of time must be equal to V0 multiplied by exponential of, let's just use the simpler notation, e to the power d CSTR times d. But if I know what V is, then I know what the flow rate should be, which means that F or at any time, which I know must be equal to dV dt. This is the first thing that we arrive from the total mass balance. That has to be equal to, you can see that it is V0 multiplied by this derivative, but this derivative is nothing but d CSTR multiplied by e to the power d CSTR times T. Okay? So essentially, if you operate, this is the key. If you supply the flow rate at this exponentially increasing rate, then the volume will increase in this exponential way. But if the volume increases in this exponential way, that means 1 over V dV dt is equal to dCSTR. So you'll get exactly the same steady state that you got in the chemostat. And this is becoming increasingly common in the biotech industry. So, you go to a CSTR, you run it at many different dilution rates, you optimize. Once you optimize, you come back to the industry, you run it in a fed batch. As I told you today, the industry still prefers to operate with fed batch reactors and then use that optimum DCSTR to operate in this way. So that takes care of the first claim. Now, the second claim, which is a little bit more tricky. Okay, so let's get to the second one. The second one says that constant fed batch cultures, they trace the steady states of by trace, actually, once again, they simply replicate the steady states. But maybe I should simply say not trace, but replicate. They replicate the steady states of CSTRs over an entire range of low dilution rates. So in an exponential fed batch reactor, we were able to replicate the dilution rate, the data obtained in a CSTR at a particular dilution rate. When we run the fed batch culture with constant feed, then what you actually do is, as I pointed out in the figure, what you will do is you are effectively starting off at a low dilution rate and essentially tracing all the steady states that are observed. As what will really happen is your D is slowly declining, and as D slowly declines, you observe all the X, the S, the P, whatever protein, whatever you have in a CSTR, you will trace them moving to the left. So to show that, let's first of all focus on what is happening to this quantity D, right? What is happening to this quantity D in a constant fed batch reactor? Well, let's take a look at. So, first thing to ask is, so the first thing I want to show is that the dilution rate in a constant, in a constant fed batch reactor is always decreasing. The dilution rate is always decreasing, right? In the exponential, we fixed it. But in a constant fed batch reactor, it is always decreasing. First, let's do it mathematically, and then physically it'll be obvious. So, well, what's the dilution rate? The dilution rate is, we called it F of T divided by V of T, right? V is also changing with time in a fed batch reactor. Well, we're dealing with a constant fed batch reactor, right? We are dealing with a fed batch reactor in which we are deliberately maintaining F to be constant. So now F is constant. That's what a fed batch reactor is. But is V constant? Obviously not. V will be what? V will be V0 plus F times T. I mean, I'm simply using this equation that I this is the equation that I'm using. This is the equation that I'm using with constant f, with f of tau to be a constant. That will just give me V0 plus f of t. So essentially, the volume at any particular time in a constant fed batch reactor, right? I mean, I can show this graphically. If this is time, then essentially your volume is growing like this. This is V0 and this is V0 plus f of t. This is volume as a function of time. And flow rate is, of course, always constant. This is your flow rate, which is f, constant. Now that means that your dilution rate is obviously coming down as a function of time. You can see it, mathematically. Now, can you see it physically? For example, if I have a reactor, so basically this is saying, this relationship is saying that the smaller the prevailing volume in the reactor, right? So we are dealing with a constant flow rate. Keep in mind, the numerator is constant. It is only the denominator that is increasing. Now, supposing this flow rate is fixed, and let's say this is 10 milliliters per minute. Now, if I have only 100 milliliters in the reactor, so let's say this is 100 milliliters, then a flow rate of 10 milliliters per minute will dilute that small volume quite rapidly. But once I have grown my volume to, let's say, 1000 milliliters, then the addition of the same 10 milliliters per minute will not have such a strong dilution effect. So the larger the volume, it is not surprising, the weaker your dilution effect. Is that part clear physically and mathematically?
Yes, sir.
Yes, sir.
So now so now you understand that the dilution rate is changing very, very slowly. As a matter of fact, it's convenient to write it in the form. If you divide this by V0, you write this as F over V0 divided by 1 plus F over V0 multiplied by T. Then, F over V0, this this can be written as D0 divided by 1 plus D0 times time, where D0 is defined as F over V0, or physically, this is the initial dilution rate. Okay? So far, so good. Now, so at least you understand the first part, that in a constant fed batch reactor, you are starting at time t equal to 0. So let's just draw this. What is this going to look like? This is going to look like this. This is your d as a function of time, and this is time. Initially, you have a d0, and then as time grows, it decreases hyperbolically, right? So, for example, at t equal to 1 over d0, this will be equal to d0 divided by 2. So when time, if you put time equal to 1 over d0, then you can see that what you will get is essentially d0 divided by 2. So d0 is a measure of the speed with which it is coming down as a function of time. But clearly, d is dropping from d0 continuously as time progresses. And physically, the meaning is obvious. Now, the next question we ask is, well, so what does this mean? Now, it turns out that if the speed, right, if now we're actually asking the question, if the rate of change of the dilution rate is small, right? If the rate of change, so now we are going from the value of d as a function of time to the rate of change, then yeah, we can assume that the reactor is always in a quasi-steady state, is always in a quasi-steady state. What do I mean by that? So going back to this picture over here, we're starting from some D0, and I'll do it in the red pen. So now we're starting from D0 and going down to the left side. Now suppose this change is taking place very, very slowly, right? So slowly. So I mean, first just imagine if we move fast, then what happens is that the system does not remain in a steady state simply because the system doesn't have time to adjust to the changes in D. But if I change it very, very slowly, so slowly that all the processes that are taking place in the reactor have time to adjust to the change. So, say for example, the growth rate changes on a time scale of, let's say, 15 minutes. But I move this light at an excruciatingly slow rate. Then the system remains in a steady state because all the variables have enough time to adjust to it. I mean, um, is this idea obvious to you, or do I need to expand on that? When the change of a parameter takes place slowly, then the system remains in a steady state. Is that idea clear to you or not?
Yes, sir.
So can you please repeat that?
I mean, so what I'm saying here is that, you see, if I changed the value of D suddenly, right, the system would depart from steady state. Why? Because let's say I change the value of D from D equal to 0.1 to D equal to 0.01 with one fell swoop. Then the abrupt change in the parameter value means that the system has to suddenly depart from the steady state it was
Yes.
at before it goes to the new steady state. But if I move from D equal to 0.1 to D equal to 0.01 over a period of 20 hours, right, really, really slowly, then it will remain in steady state all the time during its motion. And it will essentially replicate the steady states that you would have observed in a chemostat, where you are seeing real steady states. So these steady states that you observe when you are changing D very, very slowly, they are called quasi steady states, like almost like a steady state, right? Because you're changing it so slowly that the system is getting to adjust to it. So if the change is very, very small, is, I should say, actually sufficiently small, then we can assume that the reactor is always in a quasi steady state, and therefore, it's just stopped responding. Is it because they've run out of? Oh no, it's because of this. So, so, uh, it's always, the reactor is always in a steady state, and the FBR, the fed batch reactor, therefore simply replicates or traces the steady states of a CSTR. Um, of a CSTR between I should say actually not between, but all the steady states, say going downwards from D0. So all that's happening is you are going down like this to the left, and the system will basically show you these steady states. This value of X, these values of S, product, whatever protein, whatever you have in the reactor, you're simply replicating it. So if that part is now clear, you can basically see what's happening. So before I do that, so you can basically see that if I am operating over here, supposing the conditions of the Monod model are valid in my CSTR, then in this low region, you know that in this low region, you from the theory of the CSTR, you already know that in this region, which is low D, X is approximately equal to YSX times SF. All the substrate is consumed to produce biomass. I'm ignoring maintenance. Okay? And S is actually much less than SF, right? And you also know that S basically is equal to, it will actually be Ks multiplied by D over mu M minus D, right? And if it turns out that D is quite small compared to mu M in this area, then actually approximately equal to Ks multiplied by D if D is much less than mu M, right? So if your D0 is already quite small compared to D, and you're going on the left, moving further towards the left, then D is going to remain kind of small. This may very well be the picture. So what will you observe? Well, this is giving you the variation of time. So how do you solve it? So basically, if you want real numbers, close by giving you real numbers. So what does this mean? What this means is, I should actually make this more precise. What this assumption really means is that when I say that the system is in a quasi-steady state, uh, mathematically, what I mean is that essentially you have this picture. Actually, your equation was dx dt equals mu minus d times x. But dx dt is approximately equal to 0. Okay. Similarly, you had the equation 0, sorry, that is, the hell is, okay. So you also had the equation ds dt equals d times sf minus s minus rs times x. This is also approximately equal to 0. So the system is always in a steady state, right? All the time you will have mu equal to d. All the time you will have the relationship dsf minus s is equal to rs times x. So this is basically a mathematical explanation for the fact that the constant fed batch reactor, as it moves slowly to the left, in accordance with the temperature dependence d of t. So keep in mind, this d is not constant. This d is slowly decreasing as a function of time according to this dependence over here. D is slowly decreasing. But even though D is slowly decreasing, all these relationships are obeyed. Mu remains equal to D of T, and D of T multiplied by SF minus S remains equal to RS times X. And since all these equations are valid, you are basically solving just a Monod model, right? So essentially, what is going on? You will find that essentially, for example, if the Monod model is true, you have S equal to, you had the relationship Ks multiplied by D over mu m minus S. sorry, mu m minus d. Just replace this by d of t and d of t, because the equations are the same as the ones that are observed in a chemostat. Then that means if I solve for S and X and so on and so forth, so essentially X will be equal to YSX multiplied by SF minus S, right? But I already know S as a function of time, right? So I already know S as a function of time from the previous equation. This is giving me, this is S as a function of time. This is giving me X as a function of time. So this is telling you that essentially as the dilution rate slowly changes to the left, just plug in the value of D, it will tell you what the value of S is. And you can similarly get the value of X because you know S of T. And similarly, you can get the value of P and so on and so forth. Is that part clear?
Yes,
Yes, sir.
sir.
Yes.
Uh-huh. So, and if I might add, just as a last point, uh, this all this mathematics is really showing to you that you are essentially tracing the steady states of a chemostat at a speed that corresponds to the rate at which D is changing, or in fact decreasing gradually. That's all there is to it. So, what will you actually observe in the real world? That just needs to be fleshed out. Now, in practice, the way you run a fed batch reactor is actually you don't immediately run it in the fed batch mode. In practice, the way they run it in the industry or even in the lab is as follows. So, for the first few hours, you run it in the batch mode. So, you run it in the batch mode, meaning if this is your reactor, actually, I should just draw the picture here. That means that you are running it essentially with no inlet and no outlet. Um, so there is no inlet and there is no outlet. It's not responding. Okay. And you allow the cells to grow. So this is the growth of the cells. This is exponential growth. They're coming up like this. And the substrate concentration is kind of coming down, 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 down. When it is nearly equal to zero, right? That's when you switch into the fed batch mode, means to the batch reactor. Now you suddenly add an inlet stream coming at a very, very low flow rate. This is how constant fed batch reactors are done. So what happens is as soon as you switch over, right, then so here you switch over to fed batch. And when I use the term switch over to fed batch, I simply mean that from a mode where you had no inlet and no outlet, you have now switched to an inlet. That means you suddenly start introducing the feed going in. So what will happen? Well, it'll settle down to a particular value of the substrate. There'll be a small transient in between, and then ultimately it will adjust to a value of X, right? And the substrate concentration after a transient will adjust to a value, which I shouldn't say a value, the value of S will decrease continuously. Actually, if you work your way, you will see that this quantity is a very, very, S of t is slowly decreasing with time. Okay, but it's a very, very small number. So small that this quantity is equal to zero. So YSX will be essentially equal to YSX SF. So what you will find is, I should correct this graph. And then this quantity will kind of decrease, remaining slow. That's the picture that you will get. So keep in mind that X is almost constant. But X is constant, and this is all under the assumption of Monod's model, no maintenance. If there is maintenance, then X will start to decline after a while, because in the maintenance model, you know that X actually kind of goes down over here. So as D goes down, X will start to go down. It all depends upon which model is a better representation of what's going on in your system. So X is constant, but keep in mind that X times V is going to grow. Is growing, yeah, linearly. Why? So that means the total amount of biomass in your reactor is growing linearly because X is constant, but the volume of the reactor is growing linearly. And that shouldn't surprise you, because in a fed batch reactor, you're not allowing all the biomass that is growing to get out. So it's going to grow. All that stuff is collecting inside the reactor. So unlike so concentration is constant, but the amount is not constant. In a continuous reactor, both the amount and the concentration are constant because the volume is constant. Whereas in this case, the total amount is growing linearly. So I think we'll call it a day there. I think that covers whatever.
Sir,
Uh-huh.
sir, I had to ask a few things.
Uh-huh.
Sir, about the extra class, we had to have an extra class on Saturday, I think. You said 3.
Uh-huh.
So,
Yeah,
sir, yeah.
Go ahead. Yeah, I didn't get a chance. I mean, I had to prepare for that other course. I'm talking about
Yes, sir, the
SEM
Professor
3
James.
1, whatever, something else it's called. Yeah. So I just never got a chance to really give this lecture. But I will try to um, maybe hold it sometime this week.
Oh, sir, this week yeah, we have Vivas and everything, the majors coming. So, sir, I was just asking if you could hold it on, I think, 25 November, because our major is on 28th and 24th is the end date for our major. So you could hold it on 25 November. All our core courses majors are getting over on 20th November. So we'll have the time to do the questions and then discuss that on 25th.
That's fine with me.
Yes, sir. So okay. So I'll ask you about the time before, like a few days before 25th then.
So, and I will post questions, homework problems on fed batch cultures and recycle reactors.
Yes, sir, by the 20th, I guess.
No, I'm going to post it. You take your time. You do it whenever you want.
Okay,
but
sir.
I'm posting them. And for the 2 chapters that I have covered from Turan, this is chapter 8 and chapter 10. I think that, like I've told you, you should do the problems on your own, right? There are like maybe 40 problems. If a class of 50 cannot solve 40 problems collectively, then there is a problem anyway. So you are free to discuss them, but you will be probed on these problems.
So all 40 of them?
Yeah. So, I mean, how many of you are there? I mean, you are, in groups of 5, you work. You don't have groups of 5 even?
No, so like we haven't formed any groups as such. No, I'll have to tell the class then, and then.
I mean, I have been saying from the beginning, I have no problem if you work collectively.
Okay, sir.
I mean, I don't care if the whole class gets together and discusses the problems on a WhatsApp group or this channel or wherever. How can you not, as a group of 50, get together and solve 50 problems in 3 weeks?
Sir, we have the majors and everything right now. And
No, but I've been saying this for like the last 4 weeks, right? I said when I did chapter 8, I said solve the problems. The solutions are available on the web. I mean,
so we can.
This is a joke, man. I mean, you can't even look at solutions and figure out how to
we
do a
can.
problem.
So we can do that. Yes, we can do that. But then the assessment wouldn't be as a group, would it be?
No. But when I hold the Viva, I can tell what you know, right?
Okay, sir. Yeah. I get that. Yeah, we can do that.
5 minutes.
Yeah, we can.
5 minutes, and I can tell whether you really know what you're doing. I don't need to And so trust me, your vivas will be not as long as last time. Last time I gave almost 20 minutes to each individual, patiently seeking whatever you could say. But this time it will be a bit shorter because I have a much larger pool to interview. I think I interviewed 45 people over a period of 2 days.
Yes.
So I need 3 days. I mean, I've kept 3 days, but they will be shorter. So please be well prepared. You know, you're being asked to answer questions that you have already done.
Yes, sir.
And if that is still something you can't handle, then we have a problem. But it will not be like, ये number कैसे calculate किया तुमने, right? I will ask whether, I mean, my questions will be aimed at asking whether you really understood what you were doing in the problem. Okay? All right?
So can it at least be 10 minutes for everyone? I'll schedule it as such. Yeah. And
it will be 10 minutes. But all I'm trying to say is in some cases, it will stop at 10 minutes.
Yes, sir.
I mean, last time I gave pretty much 20 minutes to everyone, including a lecture, to sort of pay attention to the course and do this and do that. This time, none of that. I'm just done with it and moving on. Okay?
Yes, sir. Yes, sir.
All right.
Sir, another thing, sir, we just received a mail saying that the SBL 100, the practical courses will be held in December. So could the department also hold the courses in December? Lab courses?
No, I think I just, did you get an email saying the lab courses will be in
No,
December?
not the SBL 100 lab course will be held in December. They're doing that. The CMP 100 course for 2020 batches being held in December, and the engineering physics. Just wanted to ask you, sir.
No, I was told by the head that the course, he has not received any intimation saying any courses can be done in December because onboarding will not be done by December.
Yes, sir.
If the onboarding is not done, how can I hold the labs in December?
So, but if the onboarding is done, we can, right? I mean, I think they'll be opening the campus in December. It seems like that.
Not to. So the email I got from the head was. So actually, let me be honest with you. You know, it cannot be that we keep sitting waiting till the end of November to find out, and if they say yes, we are opening it up, because I mean, I should have clear guidance, and the reason is that to conduct these labs, we have a new lab assistant who needs to be trained. He's not trained. So to me, it seems that 90% chance is that it will not be held in December. Because I mean, from the head, the thing I'm getting is no, he has received no guidance from the institute yet.
Yes, sir.
So that being the case, the labs may be held next year.
Okay, sir.
Okay. All right. So see you on Thursday.
Fine, sir. Thank you, sir. So just a second, sir. Thursday, do we have a class? Because
yes, Thursday we'll have a class. Thursday is a working day.
Cool. Okay.
Last teaching day Thursday.
Cool. ठीक है.